So K3FeCN6 complex we will take it. So oxidation state of the central metal ion is +3. We have Fe +3 here, right? Fe +3 here. That means it is a 3d5 system. Because it is 3d6 4s2, 26 atomic number, 3 electrons we have removed, hence it is a 3d5 system. IUPAC name and all we have done it. Potassium hexacyanoferrate 3. Potassium hexacyanoferrate 3. We have done the IUPAC and all. The important thing is we just have to predict the hybridization and the geometry first. Hybridization and geometry, right? Hybridization and geometry. Hybridization is D2sp3 students. Keep it in mind, it's a strong ligand. Cyanide, carbonyl, triphenyl phosphane, NO2 minus will be coming at the, the top end of the series, top end of the spectrochemical series, and it's anyhow octahedral complex. Octahedral complex, right? Octahedral complex. One thing we have done it. The second aspect we need to take care is it is an outer orbital or inner orbital. I'll write it here itself, since there is an involvement of the inner d orbital, or since it is a strong ligand, I can say it is a outer orbital complex. Outer orbital complex. Additionally, I can put one more point. Since there is an involvement of the strong ligand, I'm sorry, it's not outer orbital, sorry, it's an inner orbital complex, right? Since there is an involvement of the inner d orbital and it's a strong ligand, I can say it's a low spin complex. Low spin complex, right? So we can calculate the magnetic moment. Before that, what has to be done is we just have to get an idea regarding what is the electronic configuration, right? Stability also, it's highly stable. Why? You have a strong ligand, highly stable complex. So, and electronic configuration, if you have to write it, that is, it's an octahedral complex. Splitting is T2G first, then we will be having Eg. How many electrons we have? We have 5 electrons in our hand. First we will fill 1, 2 and 3 in the T2G orbital. We will pair this because we will not be going up, because important thing is it is delta naught is greater than pairing energy in this case. They may ask in which of the cases the delta naught is greater than pairing energy. So complex having the strong ligand will always be having delta naught greater than pairing energy. So we will pair it, that is why it is T2G5, Eg0 is the electronic configuration, T2G5 and Eg0. CFSC of the complex is, that is T2G5, that is minus, how do you write it, minus 5 into 0.4 delta naught, minus 5 into 0.4 delta naught, or minus 2.0 delta naught is our, the crystal field stabilization energy, or I can write as minus 20 dQ is the crystal field stabilization energy. If you look at the number of the unpaired electrons, students, that is, you have only one unpaired electron. Number of unpaired electron, you have one unpaired electron. One unpaired electron. So since there is an unpaired electron, I can say the molecule is paramagnetic. Molecule is paramagnetic, right? So molecule is paramagnetic. Additionally, what we'll be writing, you will be calculating the magnetic moment. How do you calculate the magnetic moment? Magnetic moment is square root of n into n plus 2 Bohr magneton, that is square root of n into n plus 2, 1 into 1 plus 2 Bohr magneton, that is square root of, that is 3 close to 4, 4 square root is 2, I can write it as 1.8, approximately 1.8 Bohr magneton, 1.8 to 1.9, the value will be coming around 1.8 Bohr magneton. Is it clear? So this is the story of this particular complex. That is, various aspects of this particular complex we have covered. Anything could be asked from IUPAC nomenclature to the end magnetic moment. Anything could be asked from this particular complex. Very clear. We'll take few more complex. and we'll bind it up, students, from the octahedral side. For example, I will take manganese complex. Mn water 6 times, Mn water 6 times 2 plus. Or I'll write it as sulfate. How do you name this? Hexaequa manganese 2 sulfate. Hexaequa manganese 2 sulfate. Can we go one by one? Its hybridization is sp3d2 and geometry is octahedral. Geometry is octahedral, right? It's a high spin complex. It's a high spin complex, and since the outer d orbitals are involved, it's a sp3d2, outer orbital is involved. It's an outer orbital complex. Outer orbital complex, and it's a outer orbital complex. It's a less stable complex. Less stable complex. It's a less stable complex. Very clear. So this is about the stability, outer orbital complex, high spin, and the sp3d2. Before that, the electronic configuration. So electronic configuration of this particular complex is, how do you go ahead? T2G and EG. How many electrons you have? You have 5 electrons, students. It is Mn plus 2. That means it is 3D5 system. 5D electrons you have. 3 here and 2 here. T2G3 and EG2. Because it's a weak field ligand. That means delta naught is lesser than the pairing energy. That means electron will go to the higher energy rather than getting paired. So you have T2G3 and EG2 is the electronic configuration. That means how it is? dxy, dyz, dzx, dx square minus y square, dz square. Number of unpaired electrons is equal to 5 is the number of unpaired electron in this case, and the magnetic property it is paramagnetic. Magnetic property, it's paramagnetic. Clear? It's paramagnetic. Magnetic moment, if someone asks you, that is square root of n into n plus 2 Bohr magneton, square root of 5 into 5 plus 2, that is 7 into 5, square root of 35 Bohr magneton. 35 is close to 6, that means it's approximately 5.8 Bohr magneton. It is in between 5.8 and 5.9. 5.8 and 5.9. That's it, students. Very simple. Not a difficult one. So CFSE also we can calculate. Crystal field stabilization energy is 3 into minus 0.4 delta naught plus 2 into minus 0.6 delta naught. That means it is 0. Crystal field stabilization energy is 0. This complex, that is why see that is an unstable complex or less stable complex, because there is no crystal field stabilization energy for this complex, but it is highly paramagnetic complex, having highest Bohr magneton value, magnetic moment value, right? Because all 5 electrons are unpaired. All the 5 electrons in the system are unpaired. So this is about few of the properties, how to predict the properties of the complexes and all. Instead of manganese, if it is a 4D or 5D series elements are there, despite of the fact that the ligand is weak, you are supposed to pair there, because what happens is, if you are at that point, you have to keep it in mind, students, very important. So if at all they are giving, very rarely they had given, even in the previous year, you know, the question papers and all, if you look at, even for the NCERT and all, if you go through, 4D and 5D series elements are rarely given, if at all they give. Remember, you don't have to worry about whether it is a weak field ligand or the strong field ligand. You will always be getting electronic configuration will be T2G5 in that case. That means you will be pairing the system, and delta naught will be always higher than the pairing energy, and it will be low spin complex, inner orbital complex, stable complex, because the 4D and 5D series elements, irrespective of the kind of the ligand, they will be making stable complex. These points, you know, these points are important. Keep this in mind, students, which is required. Okay, so this is all about the octahedral complexes we have taken care. Some of the applications will slip over to the tetrahedral and the square planar complex.